Now let's look at an example of using the keyboard. We're going to put the letter A in the keyboard, so that's the letter A there. It's a bit small, but if I zoom in you can see there we've got the letter A within the keyboard. Now what we want to do is we want to take the ASCII value of that letter A and place it into register R0. So in effect we're taking the information from the keyboard and we're bringing it into the CPU. So if I head into the spreadsheet, now as it stands at the moment I actually have an assembler all built up in Python, so we can actually do this really quickly in the assembler, but I don't want to show you the assembler until we've finished these couple of sections, because I want to show you where the information comes from before we actually have the assembler available to us. So what we want to do is load a value from the keyboard into the register. Now we know we've got our memory mapped IO, so we need the memory location which will go to the keyboard and pull out that value. So the load command we're interested in is this load command here. So we've got, for an example here, would be load 10, RB. So what that does is it loads the contents of memory location 10 into register RB. So it loads from memory to a register. So all we have to do is ensure that the memory location that we choose here is the memory location from our memory mapped IO that points to the keyboard. And the register RB will be the register 0. Now, according to what we have here, the opcode for this is 4. Okay, so it will actually be it's going to be 4 bits that define it, so it will be 04 for the opcode, and there won't be any register A, so that will be a value of 0, but the register B will be used. But if we're using register R0, that will just be 0 as well. So our code here is going to be 0400. So that's going to give us the command that we need. But what is the address that we're interested in? Well, we've seen whenever we work through the memory mapped IO, if you go back to that video, the addresses that we used for our 16 IO devices were at the bottom of the RAM. So if that's the RAM there, and I go and edit contents, I'll shuffle this over a bit, and if we head all the way down to the bottom, it's actually going to be down at FFF0. So that's the first IO device. So FFF0 is the first, and then it goes FFF 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Okay, so all we need to do is remember that that's the value. So I've already actually put the values in here. So the RAM location is here. If I zoom in, I'll need to shift this over a bit so that you can see it. So I can shift this over and you can see here that we've got the value 0400. So this is our load, and the position memory location we're loading from is in the very next memory location. So it's going to be FFF0. And then I've just put the end command, which is 5800. So we'll zoom back out in this and we'll actually see if it works. Okay. So if we go to the top level, now that's the right side, that's good. So we've got the letter A sitting in here. Now whenever I count through here, remember we're going to go to the ROM and we're going it's going to set up the stack pointer first of all, and then it's going to go over to the beginning of the program. So I'll just count my way through here. So you can see that the stack pointer has been set. Now, just to note here, you'll notice that the stack pointer has actually been set with FFF0. But I've just said to you FFF0 is actually the location for our first I/O device. So it can't be both, can it? But the thing to note here is that I designed the stack pointer so that before we actually put any values into the stack pointer, remember we subtracted 1 from it. So although the stack pointer starts here, the very first position of the stack pointer is actually 1 before it, which is FF EF. Okay, so there's no inconsistency here. So we've got the stack pointer set up, and you see here that it's now jumping. So that 0C00 is the jump to the first address of our RAM, and then it should pull in 400, and there you see it's pulled in the value 400. Okay, so that's our instruction to load the keyboard value into the register. So I'll count through a few of these and we'll go and see where we are within the actual unit here. So let's go, if we get into the control unit, you can see we're actually on the first, just about see it, we're on the first value of the control unit. Okay, so I won't go through these, all of them in detail, we'll just find out the ones that we're actually interested in. So you can see here it's pulled in this FFF0. So now what we're interested in is looking at the values here. So we can see the address that's going to come in here is FFF0. In this instance here, the address decoder hasn't chosen the RAM or the ROM. The address decoder has said, well, we're actually going to be using one of the I/O devices. So this has gone high, the enable's gone high. Now the I/O device it's actually chosen will be the keyboard. So if you get into the keyboard and have a little look, you'll see here that the value here is 0, this is 0, so this has gone high. Okay, so we are choosing this device and we're saying we're interested in getting the information from the keyboard into the CPU. All we need to do is wait for the clock enable to go high, and when that clock enable goes high, it will shift the value of our ASCII code, and you can see the ASCII codes already there if I zoom in a bit. So there's the ASCII code there for the letter A, and whenever the clock enable goes high, it will pass that on to the bus. Okay, now, and then the rest of the command will take it and put it into register R0. But let's go back in here and we'll zoom back in a little bit. So let's go through another value. So there you see it's worked through and it's actually put the ASCII code for the letter A into register R0. Now remember, this is actually in hex. Okay, so that's going to be 1664, so that'll be 64 plus 1, that'll be 65. So 65 actually is the ASCII code for the capital A, which we've seen earlier. So we've got a method of taking a letter from the keyboard and bring it into the machine. So if we were to continue with this, you'll see that the value A will then drop out of the buffer. And there you see the value A is now gone out of the buffer. And this is us finished. It'll move on to the next line of code, which is the 5800, which is the end. So that's us worked through our very first keyboard bit of keyboard information into the computer, and it stored it in a register. Now, as I say, I have an assembler here, and in the assembler we can actually set up a loop and we can bring in as much information into the CPUs we want, and we can save the values. We could take this value here in the register, and we could place this value in the register somewhere in memory. And then we could go and get another value and place that value somewhere else in memory. Okay, and we could bring in a whole word or a whole, a whole paragraph or a whole book, and we could place the ASCII values one after the other in memory. So we could type in, if we had a buffer big enough, we could type in a whole book here. But as it stands here, it's not in effect real time. We're actually typing it in and then running the code. What we really want to be able to do is have it sitting live, so that whenever we type it in, it automatically finds it, takes it and puts it into memory, and then when we put in the next letter, it automatically realizes that there's a letter in the buffer, and we then can go in and take that letter and put it in memory. So we can do that, but we're not going to do that right here and right now. We just wanted to show you this thing working. So that was quite a simple little thing that we can now do. So thank you for listening. I'll get you on the next video. Goodbye.